Hello and welcome to this short video about how to increase the capacity in macro networks by minimizing the internal interference. I'm Arnd Sibila and I'm working as Technology Marketing Manager at Rohde&Schwarz with focus on mobile network testing. Why we are talking about it? We all know the exploding data demand in mobile networks and that capacity expansion is a must for mobile network operators. Optimization will be done first on the macro network layer since this is more cost efficient in most cases. Today I want to discuss how to limit the internal interference in a mobile network on the basis of real measurement examples. The first action sounds a bit trivial: antenna tilt optimization. In the first slide we discuss an antenna example to show how severe the impact of a misaligned antenna tilt can be. The antenna example is here a 21 dBi antenna gain with 4 degrees opening angle in vertical direction. The antenna height is in this example is 20 meters. So if you have an antenna down tilt of 4 degrees, you have an outer cell radius of 570 meters. If you only misalign this antenna tilt by 1 degree, so 1 degree to less down tilt, you immediately get an outer cell radius of 1100 meters. So you double the radius just by a misalignment, antenna tilt misalignment by only 1 degree. And double radius means 4 times the coverage area. So if the antenna tilt is misaligned, it is too high tilt, then we run into coverage holes. This is a severe impact and we can recognize this very easily. But if the antenna tilt is too low, we have these two big cells. This creates high interference in the networks and this is not easy to determine. But of course we have means to test that. So these are two screenshots here. The left shows the RSRP, reference signal receive power, which is a measure for coverage. And the right is the signal to interference and noise ratio, which is an indication of data throughput. This measurement has been done close to our central headquarters in Germany. So if you look to the two black circles on the bottom, you see on the left side there is a low coverage area, so red and green, red and yellow color here. On the right side you see also a low signal to interference and noise ratio, red and yellow colors here. So this is pretty logical. So in a low coverage situation you often get low signal to noise ratios and low data throughputs. But the upper two black circles here you see on the left side green color, so which means good coverage. But on the right side you see a low SINR. So you see they are yellow and red color. And this is an unwanted behavior. Why this can be? So now we need to start the troubleshooting process and we are suspecting here pilot pollution. So now we're in this troubleshooting process. You see on the bottom the signal to noise ratio here for the best server, and in the red marked area you see that the best server only gets a signal to interference and noise ratio of around 5 dB. On top you see that the RSRP, which means the coverage value, is quite good, so minus 70 dBm. This is a good coverage value. But you also see that there are two colors, which means there are two base stations with such high RSRP values received by the user. And this is, here we see a missing dominance. So we have one is our best server, and the other strong signal is an interferer, is a neighboring base station or a neighboring sector. Yeah? So here this is clear, we have a strong interferer and therefore the signal to noise ratio is low. So we have missing dominance here, and this is the root cause for pilot pollution. So how can we measure this, or how did we measure this? So here you see our ROMAS software platform for network optimization and troubleshooting, and the data collection tools are network scanners. You see here the network scanner family of Rohde&Schwarz. And the scanners helps to provide the root cause for such bad experience here. Measures are finally obvious, so we need to optimize the tilt, antenna tilt, or the azimuth. Yeah? Scanners as well help validating network planning models or simulations. All networks are simulated and planned, and scanners really help to validate these planning algorithms. Next slide shows the Downlink Allocation Analyzer feature. You see different users here or different user sessions here. We see in red color the resource block usage in %, in green the average modulation and coding scheme, in blue we see the scheduled data throughput, and in pink, we see here the average number of transport blocks, or the MIMO usage, so to say. If you concentrate on the blue colored user here, we see that he is consuming 15.5% of all resources. And he generates out of that 6.5 megabit per second data throughput. And this is not too much, but because this is driven by the low modulation encoding scheme, an average of 18. You see here the green bar. If you see the adjacent user, which is marked red here, he consumes only 8.8% of the resource blocks, but he can even generate pretty much the same data throughput, 5.2 megabit per second here. And the reason for this is a very high average modulation encoding scheme of 25. You see here this higher green bar. And all this the network scanners can do by only passively listening to the mobile network. This is very important. Another means to increase the capacity in a mobile network is higher sectorization. Coming from a base station with 3 sectors, going to a base station with 6 sectors. Doubling the number of sectors, this can be done horizontally or vertically. The concept is the same. We are increasing the number of cells per area, which means we are using a higher reuse of the interface resources. This is called cell splitting gain. And we can achieve a higher capacity here, which is lower than a factor of 2 because the handover areas between the different sectors are relatively bigger compared to the 3 sector sites. The main target is here. The handover areas should be as large as necessary for making the handover functional, and as small as possible to limit the interference in the cell. Limiting the interference, this remembers us to the antenna tilt optimization. So pretty much the same instruments are used here. So network scanners and the ROMOS software for optimization and troubleshooting. Thank you for your time today. I hope I could show you how important it is to control the interference in the mobile network to improve the capacity in the network. And that it should be done effectively and could be done effectively with a very easy to operate network scanner test solution. If you want to know more, please follow the link on the following slide.